think Robert's talk highlights the significance of the data sourcing challenge. And also the fact that a lot of the data is a source of differentiation. It's going to stay proprietary. And then we have an evaluation problem because we have to understand that fact that that's kind of operating inside of an enclave. So
Absolutely.
let us take questions.
I learned a lot from the concrete problems in AI safety paper, and I like the approach of looking at it through the lens of the trials and tribulations of the cleaning robot. I'm gonna hide my mom's Roomba. But it made me think if the cleaning robot could be so potentially unsafe, how much more unsafe would it be if the robot had weapons? And yet, governments are actively researching and deploying weaponized AI with varying degrees of autonomy. And it seems to me that it'll be decades before these systems are smart enough to avoid being hacked, avoid having stupid bugs, avoid killing the wrong people. And maybe by that point, we'll be on Mars and we won't trust them with guns anyway. And so I wonder what you all think about weaponization of AI that's inherently unsafe. And then Mr. Romer, if you have any insights in how these trade-offs are thought of in government.
So I think as a previous panelist said, I don't remember who, there are kind of two separate issues here. What we might call, like abuse, and what I was calling in the talk accidents. So I think one issue with the weaponization of AI is that people could use AI to kill each other, and the wrong people could use AI to kill each other, or anyone could use AI to kill anyone else. And that's kind of a policy issue. It's not that technical people don't have anything to say about it, but that's kind of one set of issues. And then the other set of issues is that AIs could do something that we don't intend, and in particular, as you say, if AIs have weapons or they're already equipped to be dangerous, then maybe that does amplify the ability of AIs to accidentally do something dangerous when they're already equipped with weapons. So I think pretty much all I have to say is just to agree that, of course, if you equip an AI with a weapon, then in addition to the risk that people will intentionally use it to harm others, that also magnifies the risk that something bad could accidentally happen.
So I'm actually going to push back a little bit because not that AIs with weapons are not scary, because I think they are, but a number of the systems that are already weaponized that are used by our militaries every day, and you do things that aren't militarized, airplanes are largely run by software. What I'm going to ask you is what makes AI unique in terms of the assurance problem, such that it's different or special from other complex systems that have safety critical implications. So I agree that it's a problem and that software quality is a problem. That's like slide 1 in my talk. And I don't know if I want to go on the record saying this, but I'm not sure we'll ever be in a world in which we don't make software mistakes because of the software quality crisis. But what I want to ask you is what makes AI special from all the other systems that are already controlling our lives in a safety critical context, just they don't happen to have reinforcement learning in them. Which isn't really an answer so much as a question.
Well, I mean, let me just say one point here, which is that right, this is a good topic for the reception, but I'll just say that the dumbest AI system that is already in use and has been for years is the landmine or the booby trap. It's got a sensor and it's got an actuator, and there's the most trivial possible logic between them. So, I mean, and then we're just going to go further in that direction. So I think this is a good topic for the reception, and maybe later.
I mean, definitely agreed. We don't need AIs to kill people. We've been doing it for a very long time.
Okay. I would just say, I'm not going to speak on behalf of the entire government, but I think that back to my, what I try to emphasize in my talk is that proper evaluation is key for assessing these systems, whether there's a weapon on the end of it or it's a decision being made. Understanding the strengths and weaknesses of these systems is going to be key.
Very nice explanation for why AI programs are regular software and why they're not regular software. One thing that you mentioned also is, let's say, continuum of bugs. Are there examples of how you can quantify in practice how one program has less bugs or is less buggy than another? Because that seems to be kind of an important part of the formula for applying.
Right, and so there was a little footnote on that slide that said that we haven't solved this problem yet. And that in particular, I think, or at least in a generic sense, right? I think for any particular system in which I have attempted to fix bugs, I am able to come up with some kind of metric. I have yet to encounter a metric that I find satisfying that generalizes to any kind of software system. So I'll just give you an example. The first bug I ever tried to fix automatically in a real system was in a web server. And in particular, it was a buffer underflow in the handling of post requests. And the first time we ran our system on it, actually, we specified a bad objective function, and what it did was turn off post requests. It still served content statically correctly, but it no longer handled dynamic content. Now, when we fixed the objective function, this is a great example, it actually found an appropriate patch. So on the one hand, you could say, well, okay, that first patch was bad. But I'm actually going to fall on my sword in front of everybody and say, I think it's better than doing nothing. Because when you do nothing, then it's possible for an attacker to take down your web server and provide a denial of service attack. If you have this bad patch, at least we're still serving static content. If you have the good patch, we're also serving dynamic content. I can measure that in terms of percentage of requests that are being processed by that web server, right? Which is immediately linked to sort of the feature set and the requirements of the system. I'm not sure how to generalize from that idea for a web server to all systems ever. And I don't know if we will, but that's sort of the hope. But I definitely, it's one of those things that we can recognize, which makes me think we might be able to measure it.
Common sense. So I don't know if you're familiar with the word of that psych, and I kind of look at
Doug Lynette, this is CYC.
CYC.
This was an old system for like,
Was this, I always get Psych and Eurisco mixed up. Okay, this is the system that had all these kind of heuristics that would like interact with each other. Okay.
Long, long ago.
Was the Giant database. Okay, I'm not super familiar with either of those. I kind of just know the names.
Did you want to make a remark?
I could make a remark.
Please.
The idea of taking the challenge that Dario had, which was learning to generalize things like the unintended costs of getting goals addressed in general environments could actually, harness various forms of common sense knowledge bases and other kinds of scruffier or classifiers of various kinds to understand various kinds of change and how human beings would view their costs versus non-costs. So you can imagine a site-like database. By the way, it's still an active project. Most people know that. It's a new company called Lucid AI that has gone more in the direction of Tom Mitchell that I think it kind of go from handcrafted to machine learning. But in general, I mean, the big long-term dream is how do you reason generally about environments and understand how to build generatively notions of cost, for example, versus having to handcraft it.
There's a question right there.
That's what I'm saying, you give the stare.
No.
My question is to the rest of the panel, and building on what you've said. I mean, the boundary that we are drawing between typical software and AI and how we're dealing with vulnerabilities. In the past, I mean, we were able to label critical software and non-critical software and draw a boundary and apply a kind of verification that would minimize the vulnerabilities in terms of 0 days, for example, or a full authority digital engine control. It's not released with the same kind of vulnerabilities, hopefully, as is the case with, let's say, Microsoft Office. And I'm interested in if you could elaborate a bit more over the fact of having a difference or no difference between AI and machine learning systems, which have
much less number of lines of code as compared to other types of software, which may be a bit more complex to understand in terms of how they operate. But is there a critical difference in there or actually no?
So to rephrase the question, is there a critical difference between machine learning systems, or is there a critical difference in terms of the standards to which we hold it?
A bit of both, but is there a critical difference or fundamental difference between traditional software and machine learning systems into that?
Sure. I mean, one thing I've noticed, I think in my own work at Google, is that in practice, often systems that get deployed contain like a machine learning component and also a software component. And when we reason about the problems between them, I do see the problems that come from both as different, but I also see them as kind of interacting and building on one another, right? So some of the problems that I talked about that can happen with reward functions or things like that, their proximate source can be a software bug. And it's also the case that often you can't tell whether a bug is caused by a machine learning system or a software piece, right? Particularly when you have a very opaque neural net. You may see that something is, it's not doing the right thing, the classification performance isn't well, and many times I've run into the situation where I don't know whether something is a software bug or a problem with the machine learning system. And the two can interact with one another. That confusion actually increases the complexity. So very practically, my own experience is just that of having two different kinds of sources for a problem as opposed to one, and that just adding to the complexity. On how different the two are, I'm not so sure.
So just one architectural principle in software engineering is to minimize the coupling of the pieces of your system. So that's one point. A second point is when software people are evaluating software quality, I mean, we always think, all right, let's look for code level bugs. But in fact, the real badness resides at higher levels of abstraction in architecture and design. If you mess up your architecture, you're really hosed. If you get your architecture right, you've got a chance. But requirements also matter. And when you're looking at the design level, there's certain sort of patterns and paradigms. There's a web app, and there's conventional structures. There's a database kind of a system that information systems people look at. There's cyber physical embedded. There are various kinds of paradigms. In a big complex system, like a military system, for example, could embody subsystems that have, these various patterns. And so once you parse it out, then you begin to get a little bit of leverage on the problem. And I think that's kind of where I saw Claire going, which is, well, with the AI algorithms and patterns, what's the leverage that we can get from that perspective? Anyway, next question is Randy.
So mine is comment to Claire. It seems like there's a huge difference between a bug because you didn't check for the size of some buffer versus one where your system didn't even anticipate the possibility of orange cones in construction site. And the former is just a pure, straightforward programming bug that's easily fixed, and the latter is really a design error. And I think in systems that interact with the physical world, which is mostly what we're talking about here, the design space, the potential operating conditions that can encounter is so huge relative to, say, network software or sort of more constrained traditional software. It seems to me like the error issues are as much due to that as to the fact that it's an AI system.
So I agree with you that in the sense that I don't think that the shape of automated repair to AI systems is going to be apply a 3-line patch to something. And I think that part of the challenge in developing techniques to fix problems in AI is figuring out what the operators look like. But at a very high level, conceptually, I think that they're actually very similar, which is a failure to consider a corner case in your operation, because we see this in software practice, which is to say that highly tested code doesn't tend to have bugs, right? I mean, those are the things that the humans thought about. Bugs are very common in exception handling code because it's rare for humans to test them. So it goes back to this known unknowns versus unknown unknowns. The things that the programmer thought about, the programmer likely did correctly. And so that, maybe the analogy is not helpful, but that is fundamentally the problem with the Tesla, right? Which is that we test it in San Francisco, where it never rains, I guess, in the winter. And then as soon as it's wet in Seattle, oh no, we didn't think about that, right? So will a patch for that look like 3 lines? I don't think so. And I think we need to push the boundaries of what fixes look like. I mean, if it's a question of relearning part of the model that relates vision to steering, and if that's sufficiently modular that we can do it without losing confidence in the correctness of the rest of the system, then that's great, we can fix it automatically, so long as we appropriately recognize that this is a situation we don't know what it should do, and we have a good way to figure out what it should do to help relearn that training situation.
Dario?
Yeah, I definitely want to add that I think this point about modularity is very important, right? So testing of software is based on the notion of modularity. In fact, the entire design of software is based on the notion of modularity. And as both of you mentioned, there are issues with modularity in AI, and I'd be remiss if I didn't mention that there's a research program which I didn't much talk about in my talk, but that some of my co-authors are interested, which is what you might call machine learning with contracts or modular machine learning. And I think this is a very interesting. Leon Bateau and some other folks have worked on this, and this is the idea that can you take this machine learning system, which I think some of the problems that we're having with it is caused by, well, there were a bunch of interacting systems, something went wrong, and there's not even a meaningful concept of localizing it. Can we break machine learning systems into pieces where each piece has a role that it's fulfilling, a contract that says that its error will be this if its inputs are that, and so that we can trace errors between the systems. And I don't know if this is possible or not, but definitely I think very good people are looking into it. I think it's a very promising area of research.
So just one comment, I want to go back to Randy's point about the orange cones, which is kind of the frame issue. So we always hear about V and V. What is V and V? V and V is verification and validation. These are actually 2 very different questions that you ask about your system. Verification is it doing the thing right? And the validation is it doing the right thing, right? And so if you're not seeing orange cones, then there's a question about whether it's doing the right thing. And I think when we talk about AI safety, when we're talking about AI systems, AI embedded in a system, and the system is in situ in some operational context, then we really have to make sure we're thinking about the validation question pretty carefully. So I think we are really about to run out of time. Let's just let Eric make a final remark.
World, and that is we're building larger, complicated AI systems. It's getting into not just machine learning, it's planners and there's receivers and sensors and there's some machine learning in there as glue in some places. And these systems, when they run in real time, have stochastic properties, and you end up with some interesting understanding, synchronization, parallelism. So bugs come at a level of abstraction at that point. And contracts can help with this, but you end up with the need to do reflection of various kinds of control and that reason between components in this larger symphony of integrated AI problem. I'm just saying it's somewhere between your thinking and
No, and I don't want to sound like I'm being flip and oversimplifying sort of the tendency, and I feel bad about it. It's something I'm working on. To oversimplify the complexity of these systems, because I do believe that they are very complex, and that a lot of the bugs are very complex. But I think the point is just that what we've learned is that bugs have properties, systems have properties in terms of the kinds of mistakes we make, and they are very regular. So even though there are stochastic properties, even though they're very complicated, there are features to the kinds of mistakes that these systems can make, and we can learn from those features in sort of a feedback loop to help identify when we see that kind of bug and figure out what the kind of fix is.
Here is that we're seeing massive maneuver happen at an unprecedented scale with the distributed things that are happening. But we understand mass and we understand maneuver pretty well. It turns out it's the switching between and accumulating resources. Now I'm using those resources. It's the set and the reset when we don't have as much information yet. And these microservices are some of the things that people are looking at to help in that switching problem. It's kind of the bad news for you is that these massive maneuver, we have a lot of data. We have the data that you need to be able to fix the bugs there. It's a good engineering problem. it's almost like these physics-based problems where we're doing the switching. And there are different types of problems that require different solutions.
Very short remark.
Yeah, so just a thought and comments, if you wish. It seems to me it might be worthwhile to contemplate how AI gets integrated into traditional safety engineering concepts and processes. So I'll name three. Hazard analysis. Haven't heard about that today, and it seems to me that a safety initiative begins with hazard analysis. There's Nancy Leveson's sort of STAMP framework of socio-technical systems for controlling the behavior of complex systems to keep them within appropriate behavioral bounds, extending from legislatures all the way down to manufacturers or regulators. And there's the issue of safety assurance cases. Right? If you go to the FDA or FAA, these places with safety mandates, then you have to define your hash defines, and you have to bring in a case that convinces them that your system is safe, whether or not the AI inside the system is itself highly reliable.
So I just want to thank Kevin for that remark. The last session tomorrow brings in some folks who are involved in the practice of systems engineering and safety engineering and have thought about it, mostly in the context of building robotic and autonomous systems. But that is one of the three perspectives that we're looking at tomorrow. But there's a fourth perspective that I didn't mention, which is food. And let me just tell you, pick up one of these. The reception, there will be enough food there for your dinner, okay? So I'll see you down there.